Okay, so this is the beginning of the third week. I sent out an email message. All of you should have gotten that. If you're not getting email messages from me, we got a problem, okay? Please contact me. We have this, I think it's every 2 years, this thing called a curriculum review here where our sponsor comes and checks everything out. It's important because we get money. Our department gets money from the sponsor. So there's no way that we can meet Thursday at 8 a.m. I have to give a presentation during that hour, sometime during that hour. So we should be able to meet it Thursday, right? Our normal laboratory time. There's no laboratory time this week. We should be able to meet in here. I have to clear that with Professor Colson, who has a class in here, but I think that'll work out. Is everybody clear about that? So it'll be 3 p.m. Pacific time this Thursday. It'll be a problem session. Okay. So we're finally going to finish chapter 5 today. And we're going to talk about decibel scales. You've all heard of that. And a little bit on transducers. Just enough to get us by this course. The whole next course, the 44-54, the whole course is dedicated to transducers, right? Okay, so to begin here, amplitudes of sound occur over a huge scale, from very quiet to very loud. To give you an example of that, we can hear as low as about 10 to the minus 12th watts per meter. And pain occurs at roughly 100 watts per meter. So that's 14 decades. That's huge. So to deal with such a big range like that, it's natural to use a logarithmic scale. And I'll talk more about that as we go along. But you all know that that's a way of compacting very large scales if you take the logarithm. It makes it very manageable. Here's another reason is that we perceive loudness, we hear loudness logarithmically. We really don't hear proportional to the intensity. We hear proportional to the log of the intensity. Why that is, what I believe is the reason, I'll mention it later. But let me show you the idea here. Suppose we're plotting intensities here on a linear scale, okay? And we're just going to do this in dimensionless units, right? So here's some intensity of 1. We'll just call this intensity 1. And let's say this is twice the intensity, okay? If you hear a sound at this intensity and then hear a sound at this intensity, you're going to say that this one's louder, and you're going to perceive it as being louder by a certain amount, all right? If I then go to 3 times the intensity, I go from here to here, you won't hear that as the same amount as going from here to here. You'll hear it as less. I have to go to 4, okay, for you to hear the increase in loudness here. For it to sound the same as the increase here, you've got to double this intensity, all right? So the way we express that, these are not these equal loudness levels here. You know, the loudness going from here to here, the change in loudness here is the same in the change in loudness here, and it's the same in the loudness here. It's not, these spacings aren't linear. They're not equally spaced on the intensity scale. But they are equally spaced on a logarithmic scale. The logarithmic scale doesn't uniformly compress things. It compresses higher things more than it does, you know, information down here. So we can see this here. It's very simple mathematically. You can see that this sequence here is just 2 to the n, right? So the intensity here is equal to, in dimensionless units, or proportional to 2 to the 0, which is 1, 2 to the 1, which is 1, 2 squared, which is 4, okay? If we take the logarithm, of this, the logarithm of the intensity, the log of anything to a power is just that power times the logarithm, right? Standard fact about logarithms. So you can see here that when we're looking at the logarithm of the intensity, as we go from one level to the next here, you know, from 1 to 2, or from n equals 1 to n is equal to 2, there's a change in frequency of the log of 2. When we go from 2 to 3, It's the same change. So these intensity levels here, which increase geometrically here when you plot it with intensity. When you plot it on the log scale, these are going to be all brought down and they'll be equally spaced. So that's what we mean when we say that we hear logarithmically in amplitude or loudness. And the same thing happens in frequency. Yeah?
Is that just specific to the human ear, or is that of all things that receive sound?
Oh, I don't, I mean other animals.
Sure.
I don't know, but my guess is yes. Now, for simpler creatures, I don't even know if we can call them animals, but that may not be the case, but I don't really know. It's a good question, I don't know. This perceiving the logarithm with regard to intensity, the same thing happens with frequency. So if this is a certain pitch, a certain frequency, and let's say I increase the frequency by a certain amount, and what we're going to do here, it's the simplest way to think of this is doubling the frequency. That's what I've done here. You see that I've doubled the intensity. So now we're going to replace this with frequency, okay, F. I play a certain frequency here. If I double the frequency, you're going to hear that as a certain increase in frequency, okay? To hear the same increase in frequency, going from here to the next sound, you have to double this. It looks just like this. You just replace these with everything here with frequency. And this can be demonstrated here. So this is a digital keyboard, simple one. It's 3 octaves. I'll explain an octave in a minute. So let me turn it on. Okay, so I'm going to start with a certain frequency here. So don't worry about the 0 here. Just I'm playing a certain frequency here. Now, to motivate the frequency interval we're going to do here, I'm going to go up a major scale, which you've all heard, right? All right? So what we've gone here, here's our low note, here's our high note. So I just played this and this. These, clearly, this is higher than that, but these sound very similar, don't they? Don't they sound similar to you? Yeah, this musical interval is called an octave, and it is a doubling of the frequency. This frequency is twice that frequency. Okay, so it's very much like our diagram here where this is the 0, and we're plotting frequency here. So I've doubled the frequency. And we hear that as a certain musical interval. Now I'm going to go the next step. Sorry. What I've done now is I've marched up here. And you can, and the whole point here is that that interval sounds the same to us as that interval. And it keeps going. I just did this one right here. So we're hearing the change in frequency here. We're hearing these as being equal from here to here. The frequency is not equally spaced here. It's the logarithm of the frequency. So logarithmic scales are important for several reasons. One of them is, and we're going to see this in one of the experiments. I didn't put this in here. I'm going to write it in. We're going to do an experiment involving the radiation pattern of a loudspeaker. Okay, the pattern being if you have a loudspeaker and you look at the sound that you receive at different angles. Okay, it's called the radiation pattern. And we'll actually go behind the loudspeaker too, and it'll be baffled. What's going to happen there is that the intensities are going to get to be quite low in certain places. And if you plotted this on a linear scale, if you plotted what you see here on a linear scale, you'll lose the structure down here at the smaller amplitudes. But on a logarithmic scale, you'll be able to see that. And one way to see that is, you know, on a logarithmic scale, where's 0? What's the log of 0? Minus infinity. No, the log of 1 is 0. The log of 0 is minus infinity. So on a logarithmic scale, you can't show the origin because it's at minus infinity. So what it's doing is, you know, it's not just compressing this uniformly. It's like I said before, it's compressing these more than down here. So it'll allow you to see the structure down here. And this is probably why we hear logarithmically. It's in our evolution. If we heard linearly, we probably wouldn't be able to discern small amplitudes or small, you know, smaller frequencies. And the people who heard that way, they got killed, okay? They didn't make it. It's in our evolution. They got eaten by saber-toothed tigers. That's what we sometimes say. Okay? So I don't know this for a fact, but it's a natural suspicion here, is that we hear logarithmically, so we can compress all this information, compress this huge scales without losing information down here at the lower levels. Okay, what's very common, as you know, in acoustics, you've all heard of decibels. That's what the acoustic, that's a general measure, but it probably arose in acoustics historically. So here's the first thing that happened historically is people recognized the need for a logarithmic scale and they defined what's called the intensity level. We'll call it capital I, capital L, okay? To distinguish it from the intensity, which is just I. And it's defined to be 10 times the log of the intensity. But you can't take the logarithm of something that has dimensions. That's meaningless. The reason it's meaningless is, what's the log of 1 meter? What do you think the log of 1 meter is? What's the log of 1? 0, okay? So it looks like the log of 1 meter is 0, but 1 meter is the same as 100 centimeters. So what happens when you take the logarithm of 100? You get 2, getting different answers, right? So when you take the logarithm of something in its dimensions, it has to be understood what those dimensions have to be, okay? And engineers do this. I think it's really dangerous. Physicists hate it, okay? But the proper way of doing it is we need to come up with a dimensionless number here. So we need a reference level, a reference intensity. This is just something that everyone agrees upon, or you define, and something that you're writing, like a report or a journal article or something. In this case, there are conventional numbers here that people use, as I'll explain to you. So this is called the reference level. It makes this dimensionless, and now we can come up with an unambiguous value of the logarithm. Now you'll notice there's a factor of 10 here. Why is that there? That's simply there to scale things up. So somebody was telling, I think a student came up with this just a couple years ago. The unit here is called decibels. Okay, why do they have deci in front of bell? Bell may have to do with a bell ringing. I don't know, some sound. But the reason we call these decibels, we'll get to that in a minute, is the deci there is probably because of this scalar here. This is just purely for convenience. So people might have started off dealing with this, and they found that the numbers were just too small. They wanted to increase them. They wanted to scale them up. So they just put a factor of 10 there. That's the only reason it's there. And it's probably behind the name of decibels. They probably started off with bells and then went to decibels. I don't know the history there. Please note, this is logarithm to the base 10, okay, by convention. So the units here, these are dimensionless units, but to signify where they're coming from as a logarithmic measure of the sound, we use the name, we call them decibels, okay? So here's an example. If the reference level, was that something? Oh. If the reference level is 10 to the minus 12 watts per meter squared, okay? And let's say we have an intensity level of 100 watts per meter squared. Oh, you'll recognize this? Yeah, well, let's just say we have these numbers, okay? What's the intensity level? Well, it's 10 times the logarithm to the base 10 of the ratio of the intensity to our fixed reference level here. And you can see that this is going to be 10 times the log of 10 to the 14th. I bring the 14 down, I get 140 times the log of 10. The log of 10 is 1, right? Those are inverse functions. Taking the logarithm and raising 10 by a power. So we get 140 here. And the way we write it is 140 dB. Okay? But to be sure what the reference level is. And people even do this, even when there's a very strong convention, they'll put this just to be absolutely sure, because this number clearly depends upon the reference level. So you can write it, they write it RE, standing for reference, and then whatever the reference level is. So typically what people do is, in a report or a paper, any kind of writing, they'll write this first, they'll put this in here, and then thereafter they won't put it. Okay? It'll be clear that it's the same as before. Okay, so that doesn't seem too complicated, but it does get a little complicated here, and we explain to you. Often, I think historically people dealt with many decades ago, I think they dealt with intensity rather than pressure. But what happened was, I think pressure microphones became better and better. And so it's natural now to deal with pressure amplitude rather than intensity. So we need to look at this from a pressure point of view. So for a plane traveling wave, or as we've seen, a spherical wave, this is the relationship between the intensity and the pressure. The intensity is proportional to the square of the pressure. If we substitute this in, okay, to our definition for the intensity level, we get this, okay, and now we can call this, what this is the square of the reference level for the pressure. Okay. Oh, please note, this is the RMS level. If it were peak, we would have a factor of 2 here. So this is as I've denoted here, this is the RMS pressure level. So what this quantity right here is, it's the square of the RMS reference level, pressure level. So we have this relationship between the two reference levels. So we can write the intensity level. We bring out the 2 and we get this. So here's a summary. We write it like this. Now, the number that we get here is going to be identical to this number, right? All we've done is just shifted this, instead of doing it in terms of intensity, we're shifting it to pressure. As long as this is true, this relationship between the reference levels, we're going to get the same number of decibels. But people don't call it, they call it something different. They call it the sound pressure level. All right? Now, why that's done, the main reason why it's done, we're going to see in a few minutes, okay? Now, I want to point out here that you'll notice something here. This sometimes causes students trouble in the beginning. It's not a 10 now, it's a 20. Because the 10 comes historically from dealing with intensity. It's just an arbitrary scalar. We got stuck with that a long time ago. Now, because the intensity is proportional to the square of the pressure, the 2 comes down and it turns that 10 into a 20. So whenever you're dealing with energies, electrically, this decibel measure is used in electrical circuits, right? So it's used in a lot of different areas. But whenever anything is going like the power, okay, energy, intensity, there's a 10 here in the definition. When it goes like the amplitude, you're going to have a 20. It's a general fact. Okay, so these two levels, I just want to point out right now, we'll get to the problem in a minute, that the IL is equal to SPL. The intensity level and the sound pressure level are equal as long as you use this relationship between the reference levels, as long as the reference levels correspond exactly. Now, a lot of time when you're dealing with decibels, you have to convert. You don't just calculate something like this, the sound pressure level. Sometimes you need to go the other way. In fact, it happens a lot. So how do we invert this? How do we solve for the RMS pressure level? Well, it's easy. We divide by 20. Okay, we want to isolate the pressure amplitude, RMS pressure amplitude. We divide by 20, and then we're going to raise 10 to each of these powers, because 10 to the logarithm, those are inverse functions. So when you do this, when you invert it, you get this. So we'll be doing this, using this quite a lot. And incidentally, the units of pressure are the SI unit of pressure is a Newton per square meter. That's called a Pascal. All right. In the CGS system, it's 1 dyne per square centimeter. Okay. Another common unit is an atmosphere, and an atmosphere is approximately the atmospheric pressure right now here in this room. The relationships between these different pressures. Now, we're mentioning this because, unfortunately, I mean, as a physical acoustician, I mainly stick with SI. But a lot of people they're all over the place. They do whatever's convenient. So you need to deal with these, and in other words, deal with conversions. And you'll notice here, well, you can see it here, but a bar is defined to be exactly 10 to the 5th Pascal. So it's just a convenient unit because an atmospheric pressure is about 10 to the 5th Pascal. So a microbar, we'll be dealing with this a fair amount. You can see that a microbar is 1/10 of a Pascal. Okay. An atmosphere is a little bit more than a bar. It's only about 1% more than a bar. So an atmosphere and a bar are roughly the same. But if you're doing precision work, you want to make sure you distinguish between these two. Okay, so what about the reference levels here? We can't do anything here without the reference levels. Well, what was chosen and is still used for the intensity, the reference level is chosen to be 10 to the minus 12 watts per square centimeter. And the reason they chose that is that that's about at the threshold of human hearing. It's about that's about the lowest intensity you can hear. Now, the lowest that depends upon the frequency. So this is at a kilohertz. So at a kilohertz, when you're born, okay, this is about what you can hear. And after that, it's downhill. Right? Is everyone familiar with this? It's happening to you right now. You may not, most of you are relatively young. You may not be aware of it. But your hearing just only gets worse. And even if you protect your hearing, it's going to get worse. And if you subject yourself to loud noises, it can be a lot worse. You really want to protect your hearing. Okay? So this threshold here just goes down. My threshold's way up. It's way up there. Not anywhere near that. Now we get to the little bit of a problem here. Okay? So this is the conventional reference level for intensity. Let's see what the corresponding pressure reference level is, okay? When you plug for air, you plug the numbers in, and we have this nice combination rho C. There's no need, you may not be used to this yet in this course, but you eventually will be. You don't want to multiply rho times C. You just want to recognize that's the impedance, and it's 415 in SI units. Much easier. Save time, and less likely to make a mistake. So we take the impedance, 415 in SI units, multiply by this reference level, 10 to the minus 12, take the square root, and we get 20 to 3 figures. You get 20.4 micropascal. All right, so here's what happened. I don't know when this happened, mid-century, in the 1900s. I don't know, but what happened is people started to drop. For convenience, they dropped this 20. They dropped the 0.4. And they would state it. They would, as I mentioned to you, let's go back here. So you, of course, stated, and people still do. I just did it in an article I published this year. I stated it. Where is it? okay? Now this is the intensity level. So what I did recently and what everyone else is doing is they state the sound pressure level. And they'll put, here what they put is 20 micropascals. That's the reference level. So it's clear, it's perfectly clear. The problem here, and you can see what it is these two numbers will now no longer be the same. The intensity level referenced to 10 to the minus 12 watts per square meter is not going to be exactly the same as the sound pressure level referenced to 20 micropascal because it's closer to 20.4, right? So people just put up with this. Everyone, all acousticians know, whenever somebody tries to mix, often you can just do it and not get involved in intensity level at all. You're just doing it pressure, and the reference level is 20 micropascals. Very common for people to do that. But if you do get drag in intensity, you want to realize that the two are not going to be exactly the same. Usually it doesn't matter. Usually people don't deal with precise decibel levels, although I'm sure there are people out there that do. But so you just need to be aware of this slight little problem here. Okay? And again, to make it absolutely clear, you would state this. At least in the beginning. Once you've stated it once, that's okay. The situation in water, that's air, 20 micropascals. The situation, water is very different. So for a while, there were three different reference levels, pressure reference levels. But finally, I've heard now that it's pretty well gotten narrowed down to 1 micropascal. So that's common. But again, you always want to state it once. Don't keep stating it again and again in the same document or in a presentation or something like that. Because then it gets annoying to see all this extra, RE, 1 micropascal. But it's good to state it in the beginning. Now, as I mentioned, and some of you may have encountered this, electrical, it's often, logarithmic scale is used for often electrical quantities, decibels. And again, one of the main reasons there is if you're looking at a spectrum, you want to be able to, that's a good example, in fact. When you're looking at a spectrum, frequency, amplitude is a function of frequency. You have some signal coming in that's got many frequencies in broadband, and you want to quantify the amplitude, at different frequencies there. We look at the spectrum. And if you look on the linear, this is really common to anyone who's done any kind of spectral analysis, experimental spectral with a fast Fourier transform box. It's really common. You look on a linear scale, you'll see this spectrum here. So here's some kind of amplitude versus frequency. And you can have some peaks in here. And it can be broadband too. Okay? And on, say this is 0 amplitude. Okay? And this can be nice. But often what happens is you're interested in some detail down here. So you could zoom in on the linear scale, but then there can be trouble there going back and forth between the scales. So the natural thing to do here is to take this and you put it down there at infinity. You take the logarithm of the amplitude. When you take the logarithm, you'll be able to see this fine structure down here and also see these. Now, it's not always convenient to do that, but if you're after an accurate value here, often you want to go to the linear scale. But typically, when people look at spectra like this, they're going to go logarithmic. So this is called, for voltages, it's called the voltage level. Okay, and why is the 20 there? Because it's not power. It's not that's proportional to voltage squared, right? So there's a 20 here. You got to remember that, and it's the logarithm of the voltage, and it has to be some kind of reference. Nowadays, the reference is almost always 1 volt, okay? But believe it or not, historically, and this is still around, I think there's a piece of equipment in our lab that uses this. I think this came up a couple of years ago, I can't remember. But 0.775 volts has been used, and still is in some cases, as a reference level. You might wonder, how did they come up with this? Well, it has to do with a standard. You know, I don't know the history behind this, and I don't want to know the history, but a long time ago there must have been these standard 600 ohm resistors. So, because if you're doing precise work, you want to make sure you know what a voltage is. So, what a volt is, let's say. So, how do you know what a volt is, or how do you know what a milliwatt is? Well, let me state it one way here. How did I write it? It arose from a standard of voltage. Okay, so assuming you can measure power accurately and you have you can measure the power, and this is evidently what happened historically. You can accurately measure the power. You have an accurate resistor. Then from that, you know, from the power being V squared over R, you can accurately determine your voltage. So you can get a standard for the voltage. So I guess this is what happened. This is why this was used for quite a while. And you know, people are trying to get rid of it and have been, I'm sure, for a long time. But they're not quite there yet. Okay. So that's the decibel scale, which is often used in acoustics. Anybody have any questions? Now, we're not done with the decibel scale. It's going to naturally arise in this next section here. And in particular, it comes up in the first experiment. So this is, and I'll tell you right now, okay, how do I state this? Well, let's wait until we get into it. Let's wait until we get into it. I don't think I wrote it into the notes, but I'll talk about it. Okay. Now, as I said in the beginning, this is a whole field in itself. There are people who spend their careers just dealing with transducers. And a lot of those people, I know a lot of them. A lot of them don't really care what they're measuring. They're just absorbed by the thing that does the measuring or the transmitting. So by a transducer here, we mean something that transduces sound. It either converts acoustical energy to electrical energy or the reciprocal, electrical energy to acoustical energy. So the first one is called, you can call it a receiver or a detector. And the second one is, like in the case of a loudspeaker, is a transmitter or a source. So there are people who literally spend their whole careers just dealing with this. And it's sufficiently complicated and interesting is that a lot of people just get absorbed in the transducers. There are people who, and where do those people come from? And how did they get involved in such a thing? Well, it started on most of them when they were quite young, I'm sure. But later on, what happens is, and I saw this in graduate school, it was unmistakable. There were some people who, they're doing some, this is PhD type stuff, right? They're doing some experiment and they can't buy an off-the-shelf transducer. They have to make it. So people go two ways when you hit that, right? They say, well, I'm gonna somehow find some transducer out there and modify it, or I'm gonna change my experiment so that I can use an off-the-shelf transducer. Okay, or I'm just gonna do it entirely different. I'm gonna change my thesis, my dissertation topic, okay? There are people who go that way. And there are other people who say, no, I'm gonna build a transducer. And what happens is, typical construction of quality transducers is extremely difficult. You have no idea how much effort goes into that. So I saw this split when I was in graduate school where some students just got absorbed in the transduction. And they kind of lost sight of what the transducer was for, okay, because they got so involved with it. But, you know, we need those people, right? We absolutely need those people. So, you know, they can go on to become transducer experts. So me, what I do is, and fortunately now there's enough companies out there. Often you can buy what you need. If you've got the money, you know, you can get an off-the-shelf kind of transducer. Or you can have a company do some modifications for you. They'll charge you, right? But I just want to warn you, it's not, I don't know if warning is the right word. Yeah, I guess it is. I have sometimes had to make my own transducers, and it's always been really difficult. You know, it's never what you want, and you have to fiddle with them to get them to behave the way, you know, close to what you want. So that's the subject of the whole next course, the whole course. Now, quantitatively, we need a quantitative measure of the transduction here. Going, let's say for a pressure microphone. The pressure microphone detects the pressure of the acoustic wave, turns it into voltage. We need a conversion factor. That conversion factor is not called a conversion factor. It's got a name. It's called the sensitivity. So it's natural to call it this for a microphone. How sensitive is your microphone? You know, if you hit it with a, how many volts do you get per Pascal? The greater number of volts you get, the more sensitive it is. So it's natural to call it the sensitivity, and this is how it's defined. It's universally called uppercase M, as far as I know. It's the voltage that you get. You have a sound wave of pressure amplitude P coming in, and you get a voltage out, amplitude out. It's the ratio. It's the volts per pascals, per Pascal. That's the definition of the sensitivity. For a pressure microphone in air, this is a typical value. For the experiment, what was it? What was the sensitivity? You guys remember? You wrote it down, right? Now, if you didn't, you can always go back in the lab. The distance learning students, I'm sure, have it. It must be on Jay's. Yeah, so it's roughly, yeah, it's millivolts per Pascal, right? Right. So that's the sensitivity of the microphone. Now, almost all microphones, particularly higher quality microphones, you don't just have a microphone. Okay, here's the microphone. You also have what's called a conditioner. This is a box that, here, that's a little bit more accurate. Here's, this is a box that's connected with a microphone. This box, these two things go together. All right, now what do I mean by that? Well, the conditioner does two things, almost always. Most microphones need to be powered, not all, but most. We'll talk more about this next quarter. Most of them need to be powered. So this thing has two functions. It powers the microphone, and it will also have some amplification of the signal. Often you need to do some kind of electrical amplification here to make it manageable, to send it to an oscilloscope or something like that. So it also amplifies. There's some, or sometimes people call this preamplifies. There's also a preamplifier typically in here. And the reason is there can be some distance here. And if this signal, often the signal coming out here is pretty small. Well, you can see, well, this is not fair to look at that, and I'll explain why. But often the signal coming here is very weak. If you didn't have some preamplification here, noise will be introduced in the cable going here. So there's a little bit of preamplification here. There's some here. When people talk about the sensitivity, it's what's coming out. This is all one unit. Okay? This is all one unit. Now, what happens in the experiment is that you can attenuate the signal here. We had to do this because, as Jay told you, the sound amplitude is too loud in the tube. Standing wave sound in a tube can get to be very loud, be very painful to the ear, or damage your ear. So, and not to overload the preamplifiers here, there's some attenuation. So in the experiment, one of the things you need to do is, can everybody see this? In the experiment, one of the things you have to do is you have to see what the actual sensitivity is here due to the fact that you have an attenuation here. And it's simple unless you're dealing in dB, and you're going to be dealing in dB. And then it gets more complicated. We'll talk about that in a minute. Okay. Now, again, there's a whole course on this. You're just getting just the bare essentials right here. How does this depend upon frequency? Well, you look this up in the microphone case, you know, the information there. They're just going to give you a number. Well, they give you more than that. They'll usually give you a chart, a graph. This is only valid over some range in frequencies. Every transducer, everything has its limitations, and especially transducers. People have put a lot of effort into making this valid over a large frequency range. But eventually, if you go too low in frequency or too high, this will no longer be valid. So this is only valid over the range in which we're getting what's called a flat response, where the output is independent of frequency. So imagine I have a microphone here. I'm hitting it with a sound wave, okay, of a fixed amplitude, and I change the frequency. The voltage out will remain the same. It will be independent of frequency over the flat regime here. And if you want to know what this is, it's stated. They'll also typically actually have a graph in there that you can look at, so you'll know when you start to push the limits. There's one other thing you need to know, and one other limitation here is, what if I double the pressure of the sound wave? What's going to happen? What voltage do I get? Twice the voltage, right? What if I double it again? I get twice. What if I keep doubling it? It's going to break down, right? Now, this is the subject of what's called linearity. It will no longer be linear. Linear means, you double the pressure, you double the voltage. They go together, or linear, the linear relationship there. If you go to too high of an amplitude, this will break down. More importantly, and you can live with this. You can live with being outside the flat regime. You just have to correct for it if you want to do this quantitatively. You just have to know the limitations and work with them, right? Regarding the linearity, the ratio will no longer be the constant if you go to too high of a pressure level. But something worse happens. Suppose this wave has a definite frequency coming in here. What you get out not just this frequency, but twice the frequency, 3 times the frequency. Those are called harmonics. And this effect, this nonlinear effect of getting out this whole spectrum of frequencies rather than a pure frequency, is called distortion. And it's usually not good. It's not an accurate measurement of what's coming in here. It's been introduced by your transducer. So that's a big problem when you're dealing with loud sounds. And in fact, here, and we haven't experimented with this, but we should. The reason we put an attenuation here. If you don't put an attenuation in here, you'll probably see. I don't know what will happen. Sometimes these boxes are. A red light may come on or something like that. But what you'll get out here is you'll get that spectrum. You'll get the higher harmonics. Okay, a little minor matter here. It's real simple. You notice we didn't specify, we're not really, this may look like peak amplitudes to you, right? But, because that's how we usually denote, when we write a capital P here, we usually mean that that's the peak amplitude, right? Suppose we're dealing with RMS. Do we have to write RMS here, or should we signify it? No, it's understood here. As long as you don't mix, as long as this is an RMS and this is an RMS, it's the same formula applies. You're going to get the same sensitivity. If you mix them, then you could be off by a square root of 2. So you want to be careful about that. So when we think of the sensitivity as the voltage amplitude divided by the pressure amplitude, this could be the peak divided by peak voltage divided by the peak pressure, the peak to peak divided by the peak to peak, or RMS divided by the RMS. It's all going to cancel out as long as you don't mix the different types of amplitudes. Okay, now, I don't know if we really need this in here, but maybe it's a good idea to get it in your heads. We'll talk more about it next quarter. We get this, the whole idea here is we have some pressure amplitude coming in and some voltage going out, right? What are you connecting this up to? Now, typically it's something with very high impedance, so it draws very little current, but not always. There are cases when there will be some finite impedance. It won't be a very large impedance. The load impedance or resistance, or in general impedance, can be different. If you, in general, when you're dealing with a transistor, a transducer, if you change the load here, you could change the value of the voltage. In general, it will change. And we will see that. We'll see an example, at least one example of that next quarter. So, in other words, the sensitivity depends upon the load. Ooh. So how do we handle that? Well, often this is going into very high impedance. It's essentially, infinite impedance. So it's open. It's like an open circuit, very high impedance. So the standard case is you want to specify what it is, and often it'll be we call it open circuit. That's very high impedance, drawing no current, which is typically the case when you put it into an analyzer or a oscilloscope. It's very high impedance. We have to deal with the sensitivity and level. Okay, often that's how it's specified. And here it is. And why is there a 20? Sensitivity is not in terms of power or energy or intensity. It's in terms of amplitude. So that's why we got the 20 there. Got to make sure it's there. Now, when you buy a transducer, they expect you to know this. Usually don't tell you this. Often they won't tell you the sensitivity. They'll just tell you the sensitivity level. But you can calculate it, right? You can invert this. I do that all the time. Okay. Okay. So, the basic idea here is we measure a voltage, we want to know what the pressure is. Well, from the linear perspective, not the level, just from the standard perspective, that's easy. The sensitivity is the volts per Pascal. So if I want to know the acoustic pressure, I take the volts divided by the volts per Pascal, the sensitivity. That's going to tell me the acoustic pressure. That's simple, okay? However, it's not so simple when you start dealing with dBs. So, with decibel measure. So let me give you some advice here. It's in italics. When you're dealing with dBs, this is what I do and other people that I know, okay, unless you're very familiar with dBs and use them all the time, what you want to do is you want to get rid of them. Okay, you're forced to use them you're doing some kind of calculation, okay? Turn everything, get rid of the dBs, turn everything into linear values. Do your calculations, and then if you need to go back to dB in the end, go back to dB in the end. That's the general rule. We'll see an example of this, okay? And to show you how complicated this can get, don't use this, okay? I've had students who, I guess they see it in the notes, they think, oh, I'm going to have to use this. This is an example of what you don't want to do, all right? Suppose you're given, you want to find the sound pressure level, and you want to find that from the sensitivity, you're given the sensitivity level and the voltage levels. Okay, that sounds reasonable. I know the sensitivity level, I know a bunch of voltage levels, I want to find the corresponding sound pressure levels. Well, let me show you how complicated it is, okay? First of all, here's the definition of the sound pressure level. We don't measure P, we measure V, okay? Well, that's easy. Okay, going from here to here. Now I got the. We don't measure V. We measure VL, the voltage level. So how do I beat this into the form of the voltage level? Well, I'm going to multiply and divide by the reference voltage here. I'm not changing the number, right? And the reason I do this is the log of this product is the sum of the logs. And what's that? That's the voltage level, right? So I finally get it out. Here's the voltage level. Here's what I'm left with. And now, well, this is no good because we don't have M, we have ML. So how do I get rid of M here? Well, I multiply and divide by the reference level, and then I do the same trick that I did before. Okay, again, don't do this. Don't do this at home or work unless you really want to, unless it's very important for you. Okay, but I recommend against it. It's so complicated, it's easy to make mistakes. What's this? Is that ML? Well, not really. You got to take the reciprocal. There's a -1, so you got to put a minus. See? It's endless, okay? In the end, here's what we get. If you want to convert the sensitivity level and a bunch of voltage level measurements to sound pressure level measurements, this is the formula that you would use. I don't do it. I recommend you not to do it unless you have a lot of data and you can also carefully type this into a spreadsheet if you want to. But I wouldn't even do it there. I would do it in stages. Here's how people do it. Here's an example of the standard way to do it. It's too easy to make a mistake here. Let's say we want to find SPL. We measure the voltage. This is common. And we're given a microphone with a sensitivity level. This is also common. So here's what I recommend. Get rid of all the dB stuff, okay? For example, we've got the sensitivity level. We get rid of it by inverting this. Remember, as we talked before. So I'm going to be able to determine the sensitivity in volts per Pascal with this formula right here. Okay, I'm not going to use the ml anymore. I'm going to use that. How do I get the pressure from the voltage? Obvious. Just from dimensional analysis, as we discussed before. Now, finally, I use our standard formula for the sound pressure level. This is what I do. And if I had a lot of values and I wanted to do a spreadsheet calculation, I still wouldn't use that formula. I would have different columns where I compute, go down this and do it for all the data. It's just too easy to make a mistake with such a complicated formula here. Finally, transmitters. Okay, they have a kind of sensitivity too. It's called a sensitivity. I don't know if that's a really appropriate word. They probably should have come up with a different word, but I don't know if they did. I don't think so. Instead of what's important here, instead of the volts per Pascal, now we're going the other way. This is like a loudspeaker. Now what we care about is the pressure per volt that we're putting in. So the source sensitivity is defined to be, called T, is defined to be the pressure divided by the volt, not the voltage per unit pressure, but the pressure per unit volts, because that's what's relevant for a source. Oops. So that's what I just said here. The source sensitivity level is going to be this, just like microphone sensitivity. And now we got a bit of a problem here. And the problem is already back here. Where do you measure the pressure output here? In general, it's going to be a function of distance, right? So what do you do? What do they do? Well, here's one thing that's done, the standard thing. They go in the far field. They go far away. They measure the pressure. All right? And they should tell you how far away they are, but that's kind of inconvenient. So what they do is they assume it's a spherical wave and extrapolate back to 1 meter from the source. Has anyone ever seen this before? You'll look and you'll see it. So that's how they get this pressure. And the warning here is that you may not be, it's not going to in general be a spherical wave, and the pressure that you get by extrapolating back to 1 meter from the source could be very different than the actual pressure at 1 meter. You need to be aware of that. Okay, does anybody have any quick questions? Okay, if there's any problem with this Thursday, I want to please let me know. All right? It's only 2 days away because this is already Tuesday. Okay.